Now our step number 2 is to introduce and recall actually the concept of strain energy. We are already familiar with it, but let's recall it and cast it in a form that is going to be useful for us. So in ME231, you've seen the concept of strain energy. Let's recall from linear elasticity. So I'm going to draw a stress strain curve here that is going to be associated with material behavior where deformations are elastic and deformations are small. So I'm going to plot epsilon instead of stretch. So we're just recalling what we already know, and the vertical axis is the stress. And the deformations here, I'm just going to pick some order of magnitude that's indicative of small deformations, and I'll pick that value to be 0.001, so 1/10 of 10% strain. So that's certainly not a large deformation, so let's call it small. So what we're looking at, if you like, is a structure, and let's consider a axial load that's imposed on that structure. So the structure is going to extend by a certain amount under the action of a load. The more I pull, the more force I expect to be generated, and the deformation caused is through a displacement u. The initial cross section is AI, the initial length is Li. Okay, so the stress strain curve is a line, and the fact that it's a line with slope Young's modulus, which induces the force generated to be proportional to the amount of displacement. Okay, so we would like to express the amount of work done. The work done is the work done in joules, if you like. It's 1/2 the area under the curve of the force displacement curve. And because the force is linear in the displacement, the area has a factor of 1/2 in it. So what I'm going to do is I'm going to scale the area by the force by the initial area and the displacement by the initial length. And so I'm going to divide the left-hand side also by the same quantities, AI, Li. And now I see that here I have the stress, the engineering stress appearing, and here amount of change in length divided by the initial length, we have the strain appearing. Now, this stress is related to the strain because I am in the linear elastic regime, linear deformations. I know that they are proportional. Sigma is E epsilon. Now, on the other hand, I just at this stage also remember that the strain can be expressed as lambda minus 1. Okay? Because lambda is defined as 1 plus epsilon, so lambda minus 1, stretch minus 1 is epsilon. And therefore, I'm going to go ahead and write this quantity that I have here, okay, which now I am going to define as psi, that's a large psi, and this is called the strain energy. Notice that it's the amount of work done per unit volume of the structure. So this is energy per unit volume. Okay, and the expression for that energy per unit volume, if the deformations are small, so that the stress is proportional to the strain or the force is proportional to the amount of elongation, the expression for the strain energy is evidently of the form psi function of lambda is equal to 1/2 E lambda minus 1 squared, right? So I have an epsilon there, lambda minus 1 squared, and the 1/2 carries over from there. So this is our expression for energy per unit volume that is stored in a structure that is loaded under axial loading, only normal stresses, it's intrinsically 1D structure, and those deformations are elastic and small. So we call that strain energy the strain energy function for linear elasticity. So here we're seeing two keywords. One, the word strain energy function, and two, we have the keyword linear elasticity. So this is the strain energy function for linear elasticity. This concept is general. This specifies the domain in which I will write that expression. I will specify the explicit form of the strain energy function, but you'll see that this is general. This specifies the domain within which this is going to be expressed, the strain energy function. Now, we see the word here, function, appearing. Now, that is not a coincidence. A function, what it allows us to do is it sort of allows us, a function in general allows us to generate some quantity of interest when we input a quantity of interest, right? So in this case, the strain energy function allows us to deduce the amount of energy that is stored per unit volume of the material when we plug in a certain amount of deformation that is measured in terms of the stretch. So as such, it is something that is very fundamental to the material, because the deformation is expressed in terms of some quantity that is inherently related to strain. Notice, just like strain, because lambda is just 1 plus epsilon, the amount of displacement, right, is structural, and on the other hand, the strain is eventually a concept that we consider at the material level. And so this is something that is an input that has to do with intrinsic material behavior. And on the other hand, we see a parameter here that is not a structural parameter, but a material parameter. So this is a function that tells us something very important about the material behavior. And so in particular, what we observe here, what we can observe, are two things. Okay. Observation number one. What I can do is I can take the derivative of this function with respect to stretch. Okay? And when I do that, I see that this is equal to, go ahead and do that. So you're going to see that it's equal to 2 cancels, E remains, lambda minus 1 remains. It's E lambda minus 1, which is equal to epsilon. So it's E epsilon, which is nothing but stress. So the derivative of the strain energy function, so when I say the derivative is just a function of the stretch, everything else being a material constant, when we take the derivative, we get the stress as an outcome. Now, there is another important issue, and when I take the second derivative, let's see what we're going to take. So there is only one parameter really that we are taking a derivative with respect to its lambda. I could have written an absolute derivative here instead of a partial, but again, I'll retain the partial because that is the customary approach in general. So when I take the second derivative now, the first derivative was the stress, and the second derivative therefore is going to be the first derivative of the stress with respect to stretch, and that is nothing but the Young's modulus. So the first derivative delivers us something that is very important in stress, and the second derivative also delivers us something, a material property. Observed alternatively, this is a function that clearly is quadratic in lambda, or quadratic in the strain. The first derivative is therefore linear in the strain. The second derivative is a constant, and that constant is not something arbitrary. That constant is the slope of the stress-strain curve, which doesn't depend on the amount of strain because that relation is a line, and hence, so this is a linear relation in terms of stress versus strain, and therefore the second derivative or the first derivative of the stress is a constant, and it's E, and that constant is a material property. So it's a constant slope. Let's make a note of it. Constant slope. Good. All right. So these are two important observations that we are going to make use of. So we want to talk about nonlinear elasticity, but we are doing that, eventually we're going to do that based on this concept of strain energy function. It's going to play a fundamental role. So now, making use of these observations, now we can proceed and actually do something about modeling nonlinear behavior in the context of elasticity.